right, so this is Forensic Drugs Part 2, and now we're going to get into the laws and how we forensically identify drugs. So let's get moving. So let's talk about the drug control laws. Obviously, we're going to be focusing on a lot of the federal laws. A lot of the state laws are going to vary, obviously, depending on the state that you're in. A good example of that would be things like marijuana. So I'm from Massachusetts. Massachusetts, marijuana is legal. You can actually own a certain amount on your person. You can grow a certain amount of plants in your house. You just can't sell it to anybody. Obviously, it's different than here, right? Marijuana is still considered to be illegal. You're not allowed to have any on your person. You obviously can't have a farm in your house, okay? So the laws are going to vary by state. So when we talk about the federal law, so the U.S. federal law is going to be known as the Controlled Substances Act, and it's going to serve basically to illustrate a legal drug classification system, and it was created to prevent and control drug abuse. The federal law is going to establish 5 different schedules and classifications for controlled dangerous substances on the basis of the drugs, potential for abuse, potential for physical and psychological dependence, and then obviously its medical value. Now, when I talk about these federal laws, this is one of the issues with making marijuana legal, is because of the schedule that they place marijuana in, and we'll get there. Okay, so let's talk about Schedule 1. So Schedule 1 drugs are classified by the federal government as having a high potential for abuse and having no currently accepted medical use. And the sample of what falls into Schedule 1 drugs are going to be heroin, we have marijuana, we have Quaaludes, and LSD, okay? So this is the reason why there is such a debate about making marijuana legal, is because technically, according to the federal government, marijuana is a Schedule 1 drug, which means that it has a high potential for abuse and there is no medical reason to use it. Okay, when we talk about Schedule 2 drugs, they're going to have a high potential for abuse, but they're going to have medical use with severe restrictions. Now, I know it looks a little weird that we see cocaine in that group, but if you think back in the day, they actually used to use cocaine when you went to the dentist. Obviously, they don't do that anymore, but that's why it's on this has medical use, but obviously it needs to be severely restricted. So that's going to be cocaine, PCP, most amphetamines, and most barbiturate prescriptions fall into Schedule 2 drug. When we take a look at Schedule 3, these drugs are going to have less potential for abuse, and they currently have an accepted medical use. So we're talking about all the barbiturates that are not covered under Schedule 2. Codeine falls under that category, as well as anabolic steroids. For Schedule 4, they're going to have a low potential for abuse, and they're going to have a current medical use, right? This is where we get into all of the things that doctors can prescribe to patients for certain things. So this sample list, and this isn't everything on the list, just like with everything else. We have Darvon, we have phenobarbital, we have some tranquilizers such as diazepam, which is also known as Valium, and then we have Librium. Okay, those are all considered tranquilizers that are under Schedule 4. Schedule 5 are basically drugs that show a low abuse potential, and they have a certain medical use. So we're talking about some of the opioid drug mixtures, okay? And most of them are going to contain non-narcotic medicinal ingredients. Okay, let's flip over to drug identification. So the challenge of this forensic drug identification is that you are going to need to select a certain procedure to identify a specific drug. Okay, so there are certain tests that are specific to only one drug. So if you were to get a sample from a crime scene of a white powder and you didn't know what it was, you would have to put it through all of the tests until you figured out which one it is. Okay, sometimes you get lucky and it's that first test. Sometimes not so lucky, and it ends up being the 10th test. So there are two different phases when we're talking about how do we identify drugs. The first one is going to be a screening test. It's usually something non-specific, and it's usually where you start. Okay, so essentially when you get a drug, you're trying to decide from maybe hundreds of different variants which drug this is. Well, there are screening tests you can do that will say, hey, guess what? This is in the opioid family. Okay, or this is in the cocaine family, whether it's cocaine or crack, okay? But there are screening tests that you can use that will narrow your choices of what your next test should be. After you do that, you're going to do a confirmation test that basically it is the single test that is going to specify a particular substance. So the screening test is, oh, it could be these 8. The confirmation test is, it is this one. So let's talk about your preliminary analysis. So you're going to need to use some sorts of screening tests so you can take those hundreds of variants and bring it down to a manageable number. The objective is usually using some sort of color test. So we have all sorts of tests, like we have the Scott's test, which cocaine turns blue in the Scott's test, right? But you won't know specifically that it's cocaine. It just has those ingredients that are in that particular family. But what you're going to want to look for is a characteristic color that will let you know what drug it is. All right, and we'll talk about all the different tests. You guys are going to have an activity that you guys are going to do where you guys are going to be forensic toxicologists, and you guys will try and figure out what drug it is based on the test. So when we talk about microcrystalline tests, this is just a fancy way of saying we are going to look at the size and the shape of the crystal. We are going to make some sort of conclusions about what that crystal looks like. And then we may specifically mix it with a particular reagent to see what those crystals look like. And it's just a baseline test, right? So I can say, oh, well, crack has larger crystals than cocaine. So if I look at a microcrystalline test, I can say these are smaller, they're shiny, they're rough, okay? Those types of things. It's a very general description of the actual drug, but it's a great place to start. So when we talk about confirmation determination, once we do whatever the preliminary analysis is, whether it's the color test or the microcrystalline test, then we have to do a confirmational test. And forensic chemists are going to use all sorts of different tests to identify the drug, and you want to make sure that you identify it in the exclusion of all other known chemical substances. Sometimes it is rather difficult just because a lot of these manufacturers of drugs cut their drugs with all sorts of different things. So it's a little bit more difficult to figure out what the mix of drugs is going on in that sample. So typically we have certain tests that we're going to use for these confirmation tests. The first one is one that we briefly talked about when we talked about hair and fibers. This is going to be the infrared spectrophotometry. And then we have our old friend, the GCMS, the gas chromatography and mass spectrometry machine that we talked about in the last unit, right? When we were talking about arson and how to figure out what accelerant is at the scene. And it's going to be used to specifically identify a particular drug substance. So there are two terms which are really important when we start talking about this individual identification. They are going to be qualitative or quantitative. So this is another technique that you can use, okay? But you're going to need to know what that means. So when we talk about the definitions, right, qualitative is going to refer to the identity of the material. Quantitative is going to relate to the percent composition in that particular mixture. So for example, if we were talking about qualitative, we could say qualitatively, this is a sample of cocaine. If we're looking at quantitative numbers, we're going to say, oh, well, there is 80% cocaine, 10% baking soda, 5% rat poison, and 5% water. Okay, so it's like the breaking down of the overall category of the drug, if that makes sense. Okay, so we go from the very broad, right, to the more specific. Okay, so here is an example of gas chromatography. I don't want to get too much into it, but basically there's going to be a gas phase and a liquid phase, and you are going to run your sample through the chromatography machine, and it will stop at certain areas depending on its size. We'll talk a little bit more about that when we go into all the individual types of chromatography that will be in this unit. Okay, so when we talk about chromatography, it's going to be the means of separating the different components of a mixture. Okay, so like I said, if you have a mixture of compounds, obviously they're going to be different sizes. They're going to run at different sizes. So you should be able to separate the different sizes and then figure out what the individual compound is. Okay, so the theory of chromatography is going to be based on the theory that chemical substances, right, are going to partially escape into the environment when they are dissolved in a liquid or they are absorbed on a solid surface. So there are certain different types of chromatography, which we'll talk about. We'll talk about TLC, which is thin layer chromatography. We'll talk about PC, which is paper chromatography. And then, of course, we'll talk about the gold standard, which is going to be gas chromatography. So those materials are going to have a preference for the moving phase, and they're going to slowly pull ahead, and they're going to separate from those substances that want to remain in the stationary phase. And obviously, the phase that it's going to prefer is going to deal with the chemical composition of whatever that compound is. Right? I'm sure you guys probably remember from chemistry when we talk about like dissolving like, all of those things are going to come into play when we're talking about chromatography. So this is the first set of chromatography. This is TLC. This is thin layer chromatography. It's going to use a solid stationary phase. And it's usually coated onto a glass plate. Okay, that's going to be your stationary phase. And then you're going to have a mobile or a liquid phase that's going to separate the components of the mixture. So what I'm going to do is I actually have some videos that I'm going to upload that shows you all the different types of chromatography and how to separate the three. So when we talk about the liquid is going to rise up the plate by something that we call capillary action, and it's going to cause the sample to become distributed between the stationary phase and this moving liquid phase. Because most of these compounds are colorless, you're going to have to use UV light to see the different chemicals. So normally what happens is we run the TLC and then we spray that plate with some sort of chemical agent, and then we take a look under UV light, and the different chemicals will have a different fluorescing range. The distance that spot is going to travel is going to be called the RF value. And we'll talk a little bit more about that when we talk about paper chromatography. It is applicable to all chromatography, but it's a little bit easier to see in paper chromatography. So let's talk about the gold standard, and that's going to be gas chromatography. So in GC, the moving phase is actually a gas, and it's called the carrier gas, and it's going to flow through a column. So if you take a look here at the gas chromatography machine, we're going to have a sample that's going to be in a syringe. We're going to have an injector that you're going to place the syringe in, that's going to inject the material into the actual GC. And then you're going to have that carrier gas that is in that injector where the sample first goes in. And then if you look at 4, you're going to have a column. And if you look, there are a bunch of kinks or twists in the column, right? That's basically going to be separating all of the different components in the GC. And then you're going to have a detector. So what's going to happen is as the GC machine moves, right, each molecule or the compound is going to move through the column, and each compound or each material that's in the compound is going to separate at a different rate. So that means that it's going to basically come out of the column into the detector at different times. And then obviously you need a power supply that's going to run the whole joint. Then you're going to need a recorder. The recorder is going to take the chemical picture of the compound, and it's actually going to turn it into peaks of where that particular compound came out of the GC. Okay, higher the peak means more of it is in that particular sample. And this will make more sense once we go through some of the activities in this unit. So here is an example of a gas chromatograph. So when we talk about the GC, the stationary phase is going to be a thin film of liquid, and it's going to be contained within that column. After the mixture has gone through the length of the column, it's going to emerge in all of its separate components. So if you take a look down here on the very first chromatogram that you see a bunch of peaks, right? You see a big peak here, and then you have a little peak here, and then you have 2 other peaks after that. Each of the different peaks are basically chemicals or compounds that are coming out of the GC. And if you look at the axis, it measures in time. So obviously, depending on the type of chromatography, there are going to be certain compounds that come out first and certain ones that come out second, third, fourth, and so on, and that's how they get separated. So in this first one, if you look, the pentobarbital sample came out of the GC at almost 4 minutes, and the secobarbital came out of the machine closer to 5 minutes. If you take a look at the other chromatogram, same type of thing, except we now have more compounds. So we have 5 different compounds as opposed to 3. Now, if I were to read this butyl-barbital is the first thing that came out through the column to the recorder. The phenobarbital was the last one that came out of the column and to the recorder, okay? So that's how you can separate the different compounds in a mixture. When we talk about the written record of the separation, so these 2 pictures at the bottom right here, okay, are known as chromatograms, okay? Now, the time that's required for the component to emerge from the GC column or to leave the GC column is going to be known as retention time. Okay, so that's going to be pretty much it for the GC. Like I said, we're going to talk some more about it a little bit later on, but we're actually going to be looking at some actual lab samples. It'll probably give you a better idea of what's going on. Now let's talk about spectrophotometry. So basically it goes on the principle that different substances can absorb different wavelengths of light to produce color. Okay, so a lot of the invisible radiations of the electromagnetic spectrum are going to be absorbed by substances, and the spectrophotometer can read the absorption rate. So spectrophotometry is going to be a very important analytical tool. It's going to measure the quantity of radiation that that particular compound is going to absorb, and it's going to have it as a function of wavelength and frequency so that you can compare samples. The quantity of light that's going to be absorbed at any frequency is going to be directly proportional to the concentration of the absorbing species. This is known as Beer's law, okay? We're not going to get too, let's say, into the chemistry side of things. I just want you to have a basic knowledge and set some of the definitions at your disposal. So let's talk about UV and IR spectrophotometry. So most forensic laboratories are going to use these 2 spectrophotometers to characterize different chemical compounds. The simplicity of the UV basically makes it a great tool for determining the material's probable identity, okay? But because it's a little, let's just say, less complicated than IR or some of the other methods, you're not going to get, for a lot of times, you may not get a definitive result. You're going to have to perform a UV spec, and you're going to have to do something else to get a definitive conclusion or confirmatory result. The IR spectrum is more complicated than the UV spectrum, and therefore is more likely to provide a definitive result. Okay, so let's talk about this UV and IR. So different materials are going to have distinctly different IR spectra. Each IR spectrum is going to be equivalent to what we would consider a fingerprint of that substance or that drug. Okay, there is only one chemical that's going to have that particular IR fingerprint, and that's how you're going to be able to identify it. Okay, let's talk about the spectrophotometer in general. This is going to be the instrument that is actually going to measure and record the absorption spectrum of that chemical substance. So the different components of this spec are going to be some sort of radiation source. You're going to have a monochromator or frequency selector. You're obviously going to need something to put your sample in, so you need a sample holder. You're going to have a detector that is going to convert that electromagnetic radiation into some sort of electric signal. And then you're going to have a recorder that is going to produce a recording of that signal. So essentially, we're creating another quote unquote picture of our chemical. The absorption spectrum can be done in the visible range, the UV range, or the IR range. So here's a picture of the mass spectrometry machine. Okay, so this is a mass spectrometer. Basically what happens is you're going to have a beam of high energy electrons that are going to collide with a material, and it's going to produce these positively charged ions. So if you take a look, it looks very similar to the GC, and normally it's used in together with the GC, which is why most machines are called GCMSs, gas chromatography mass spectrometry machines. So you're going to have an injection port where you're going to be able to inject your sample. Then you're going to have some sort of ionic source, and then you're going to have a basically they call it a quadrupole, which is producing all of these positively charged ions. And then you need some sort of detector. And then, of course, that's attached to a data system that's going to read from the detector. Just like the regular GC, if you take a look at the mass spec, there is a GC column that is inside the mass spec. Okay, so for most labs, it's going to be a combination GC mass spec. The sample goes to the GC to separate its components. Then it goes directly through the mass spec so that we can get a picture of the actual sample. Okay, so these positive ions are going to be separated into many fragments, and they're going to be separated according to their masses, all right? So when we talk about just the GC and making the chromatogram, they are separated by the time that it takes for them to emerge out of the GC. When we talk about the mass spec, it's a little bit more specific. Now it's going to be separated according to their masses. Now, of course, the unique feature of the mass spec is that if you carefully control your conditions, there are going to be no two substances that are going to produce the same fragmentation pattern, which means that it's more specific so that you can definitely identify that one particular compound. Here is the combination of the GC and the mass spec that I was talking about. So there is normally a direct connection between the GC column and the mass spec. Okay, so as the sample comes out of the GC, it goes directly, as the component goes into the mass spec, it is going to emerge from the GC. So we're going to go, we have the sample, we're going to put it into the GC, run it through the column, have that picture or that chromatogram, and then we're going to run it through the mass spec machine, and we're actually going to get that fragmentation identification. So it is a two-pronged process. GC first, mass spec second. The separation of the mixture's components is going to be first accomplished by the GC, like I said, and then the fragmentation of each of those components is going to produce what we were talking about in terms of that individual fingerprint of that substance that you are analyzing from your scene. Here is an example of the GCMS. Basically, what it's telling you is it is sorting out the abundance, which is the amount of that particular fragment in the sample, and then it's all separated by size. So if you take a look on one axis, you have mass and charge. You take a look at the other axis, and it has to do with abundance. Okay, so let's get into collection and preservation. So whoever is the investigator has the responsibility to make sure that the evidence is properly packaged and labeled for the lab. We know that, okay? It's like that with any other piece of evidence that you would collect at a scene. Generally, when we talk about common sense is probably the best guide. You want to make sure that you are preventing the loss of the contents, and you definitely don't want any cross-contamination because that could be a big deal when it comes to a drug analysis. Often the original container in which a drug was seized will suffice. So for example, if you're at a crime scene and you see some Valium in a medical container or a medical capsule container that you would pick up from any CVS, you can usually leave that in the container and then you'll place it into some sort of paper bag. And then of course you will label it and tag it with your chain of custody. All packages have to be marked with information that is sufficient to ensure that the officer knows what it is, okay? Because you're definitely going to want to have that on your chain of custody. It's going to be a problem if you're like, I don't know, unknown sample 1, right? You might want to put unknown white powder where it was from, just so that it is as specific as possible for the chain of custody. And that is the end of part 2 notes. So hopefully you guys learned a lot, okay? The next part of this is going to be applying all of this knowledge that you've learned. All right, I'll see you next time.